I'll repeat it. That's fine. Okay, so recording. All right, so we are recording now. So again, as I was saying, guys, for the recommender system, the last part of this is that we have the code that we saw last week, right? All of this code, we went over it. We read the data. We calculated the dictionaries, just all of that was described in the previous video. We created the matrix, right, as described in the video, normalized the data. And then finally, we stopped here last week. We did the singular value decomposition. Okay, so we've got our U, our S, and our V. So the question now is, how do we pick movies? Well, as it turns out, the way that we pick up movies is actually can be very similar to the KNN algorithm. So if you understood the KNN algorithm, we were calculating Euclidean distances. Here in this one, instead of using Euclidean distance, the code just says use a function that uses the cosine similarity. So without getting into a lot of detail, let me just simply say cosine similarity is exact. It offers the same goal as the Euclidean distance, calculating distances between things in a vector space. So that's all that this is doing. So you literally don't even have to worry about the code in here. Just use the function as is, right? And kind of disregard what's in here. Or you can also, if you feel like it, implement your own function using the KNN code that I already provided from your homework. And then here, once you have the data, you simply just print it out with this function. So this code that I provided here obviously is commented out. Just remove the comments and then you'll be able to do it. So let's now think of how you're going to perform this analysis, right? So you're gonna pick a movie. Let's say like start with a movie ID 10, The Matrix. And you're gonna say, I want the 10 movies that are most similar to The Matrix because I wanna recommend to my customers those 10 movies. I want them to kind of, pay me money and, I wanna make more money, right? So that's the goal. Now, I need the information, instead of using the information from A, which is just, if you remember, A is just this matrix, right? The matrix of 9,724 movies to 610 users, right? So 610 users or 620 users, whatever it was. So that was the original matrix, but instead of using that one, I'm going to use what singular value decomposition gives me, which is these matrices, U, S, and V, right? So those are the new matrices that now have captured the information, the relationship between the users and the movies and the ratings. All of that has been captured in these three matrices. And because there's a compression going on that we looked when we talked about SVD and compression, we can also reduce the dimensionality and just make the calculation even more efficient. Okay, so if we go back to the code, then you can see we are going to take V or U, whichever one you want. You can see that here. Here you take V. Maybe that has the representative data that you want. And we're just going to slice the top 50 principal components, or the concepts, if you will. Because we've talked about how we're going to get 620 components on U and V, but not all of those are relevant, right? So we look at the energy, also as discussed last week, to maybe pick the number, or here arbitrarily we just pick 50, which is less than 620. So basically you slice that data out, and then you're going to provide that data plus the movie of interest, and then that's going to give you the indices of the top scores, and then basically you just look it up with this function, right? So if we go back to the WordPad, you can see here, this was the original X. After singular value decomposition, we get U, S, and V, and then we slice, remember, only the K. So K in this case arbitrarily 50, or maybe let's say that by energy we calculated 64, something like that, but we slice it out. What does that mean? We disregard these concepts. They have no interest. we only care about C1, C2, C3, or C1, C2, C3 over here, right? So we also slice and disregard the rest. That makes U and V smaller, but the value is that the matrices have important data here, okay? So why does KNN work? So let's think about the movies, right? Let's say we have the V matrix over here. It goes from, let's say, sorry, I drew the wrong one. So let's think about the one that we're calling, the one that we know has the movies, 9,724, and this has concepts. I already took out the concepts, and I'm at CK, right? I took out, so this is CK, which is 50. So I only have the 50 concepts, okay? What did we say about these concepts, guys? What were they? Like sci-fi, right? Possibly romance. But this one could be Will Ferrell, right? You know, something. So what's common about these movies? So C4 is comedy. And let's just think we have these, we have these movies here. We have, the sci-fi, The Matrix, and space. Let's call one space. I don't know. So that's sci-fi. Romance, I think Casablanca is romance. Comedy is, what's a comedy? With Will Ferrell.
Step Brothers.
Step Brothers, okay. Step Brothers. Another comedy. There's a movie coming out, Coming to America. So number 2 with Murphy. So we have these movies, right? So think about it. So
Professor, your audio is messed up again.
Yeah.
University does not provide me. Does this work now? Is that better?
No, it still sounds really bad.
So bad. How about now?
Much better.
Much better. Okay, so this works?
Yeah.
All right, so let's think about this, right? So I go back to, where were we here? Okay, so I just want to do a simple example just to kind of illustrate why this would work. So although users are not here anymore, these concepts should have captured something, right? So what would you expect if concept C4 represents, amount of comedy in the movie, right? Let's say. What would you expect about, and it's scaled, right? It's normalized, it's scaled, normalized, etc. So it goes from range from 0 to 1, where 0 is, very little comedy, 1 is very high comedy. What would you say for the column C4 comedy about Coming to America 2? What value would you give it?
5, 4.
Huh?
It's a 5. It's a comedy.
Wouldn't it be higher than a 5?
Oh, I'm sorry. I thought the max was a 5.
No, it goes from 0 to 1. It's normalized. It's right.
Oh, okay. I'm sorry. So 1.
Remember, it's not a rating anymore. It is, that's a good point, actually. Remember, the ratings were those things before. Remember what this data looks like. It actually goes from -1 to 1, right? But it represents something in the vector space of comedy. You see what I'm saying?
Mm-hmm.
So what would be the value for Coming to America?
1.
Oh, 1. Let's say a 0.9, right? So
Okay.
0.9. What about Step Brothers?
0.9.
0.9, okay. What about Casablanca?
0.3.
0.1. Let's
Okay.
I don't know. Let's just go to extremes because I want to. What about for space?
I have no idea what space is about.
Yeah, Spaceballs.
Oh. So what? .8, .9.
Yeah, I actually thought that movie was really funny. All right, so 0.9. What about The Matrix? That's definitely not a comedy, right? So
Right. So another .1 or like, yeah.
yeah. Do you see this? This is kind of what intuitively, these won't be the actual values, but intuitively we can think of it. And that's why I want to point this out as that it's similar to KNN. If you think now, Coming to America on the Will Ferrell, well, it's not exactly Will Ferrell, so, but it might be the style of comedy he has. So let's say 0.4. Now, Step Brothers, somebody said it is Will Ferrell, so 0.8. You see that? Casablanca, Will Ferrell, definitely not. Spaceballs, somewhat that kind of humor, 0.4. Matrix, no, right? And then, and it could be a 0 too, that's fine. Now, romance, Matrix has some romance, I think, 0.4. Spaceballs, it is actually about some romance, romantic comedy. Casablanca, definitely romance, I think. Step Brothers, was that a romance comedy? No, probably not. All right, so 0.1, Coming to America. The first one had some romance, right? I'm assuming this one too. So 0.4. Now, sci-fi, Matrix, right? Maybe a 1.0. No, let's just say 0.9. Spaceballs, sci-fi, yes. 0.8. Casablanca, 0.1. Step Brothers, I don't know, but I'm assuming not. Coming to America was not sci-fi. Do you see that, guys? Does this make sense so far?
Yeah.
All right. Now, where does this idea of calculating distances come in? Well, what is this? What did we say about these matrices? They're vector spaces, correct? They're vector spaces. So
Yeah.
if I create a vector space, now this has 4, actually it would have 50, but because we can only visualize, I'm going to pick 2, all right? So 2 dimensions, R2. The axis will be comedy, this one, which is C4, and this one will be C1, sci-fi. You guys see that? So CY, now let's think about why we could, in fact, use distance functions here. Well, let's plot the movies, okay? So let's plot the first one, the matrix, right? We're only going to focus on this vector, C1, and this vector, C4, okay? All right, so let's think a little bit about this. All right, so the matrix on the sci-fi is 0.9, right? So that's pretty high. So remember, these go from 0 to 1, 0 to 1, okay? So the matrix in sci-fi is pretty high, but in comedy is really low, right? So it's gonna go to, 0.2, and then it goes all the way to 0.9. So about here, would you say that's where it goes?
Yeah.
Yeah, right. Okay, so that's the matrix, done. Let's look at Spaceballs. So Spaceballs also 0.8, a little bit lower on the sci-fi. And comedy is actually 0.9, really high too, right? So Spaceballs. You see that? Done. Casablanca on the sci-fi is really low, around here. But on the comedy is also very low, right? It's also very low. So Casablanca goes here. Okay, done. Step Brothers. Step Brothers has a very low sci-fi, 0.1, and a very high comedy, 0.9. So it kind of goes over here, let's say. So this is Step Brothers. And then Coming to America is 0.2, a little bit higher on the sci-fi for whatever reason, and 0.9, so about there. Now, I only did this for 5 movies. Obviously, there would be more movies. So do you see, this just became exactly a KNN type of problem. Don't you think, guys? So for instance, I tell you the movie, what's the obvious one here? If I say Step Brothers, right? Let's say that that's the movie ID in question. Because, you know, we pick Michael, right? And Michael says, well, I liked Step Brothers. Which movie would you recommend to Michael then? He hasn't seen all the other ones. He has just seen Step Brothers. So which of these movies would you recommend to him and why?
Coming to America too,
Coming to America 2, right? Why?
because it's the closest.
It's the closest one. How do you calculate the distance?
Oh, I mean, with the function that we had inside the algorithm.
Or how did you do it before?
Oh, just by eyes. Okay, yeah, just seeing what's closest.
No. How did we do it
Euclidean distance.
with Euclidean distance, right?
Oh, okay.
You could do it that way.
Yeah.
Right?
Yeah.
The exact same problem as before, as KNN. Nothing changes. It's literally the same exact problem. Calculate all the distances, sort them, and pick the top 5 or top 10. See how that's very similar to the KNN algorithm?
Yeah.
Yeah, you would measure all the distances, right? Then after that, another thing to think about is if Michael likes comedy, right? You kind of pick comedy there. Then you could just focus on other comedies, right? What's another comedy here? Spaceballs, right? You can look at the comedies here are these, right? So what are they? Spaceballs, Step Brothers, Coming to America. You can just pick one axis if you'd like, but otherwise you can pick 50 axes, calculate distances, you know, between all the points, and then pick the ones that are closest. Does this make sense, guys? Are there any questions?
No questions. It makes sense.
Now let's look at the users, right? Users is similar concept. I have 620 users. And I'm just gonna pick, you know, the top 50. So K is 50. So this is concept 1, concept 2, all the way to concept K, which is 50. All right. And then now I do the same thing. Well, I can plot every user. So user 1, user 2, user 3, ... user 620. I can plot all of them in a space from C1 to CK. What's the dimensionality of that space? Rn. What would be n equal to? Remember, the space is, the points are here are the users, right? User 1, user 2. How many of these axes do you have? You're going to have 620 samples, but what's the dimensionality of the space?
Would it also be 620?
Not 620.
Or the 50?
50, right? Do you understand that?
Yeah.
That's why we're picking the energy. Remember that what we talked about the energy. The energy tells us how many principal components are important, or just arbitrarily pick 50. Therefore, each user is represented as a vector of 50. Do you see that? Does this make sense?
Yeah.
So this is R50. So now when we plot the users, we do the exact same thing, right? So let's think about it. We have 620 users from user 1, user 2, all the way to user 620. And then here we have concept 1, concept 2, all the way to concept K, which is 50. I've already gotten rid of all of these, right? So I can just get rid of them. So now I'm here and I'm gonna plot. So again, you know, I'm just gonna pick one concept. Let's say this one is, again, sci-fi. And another one, let's say 50, or no, 40, well, actually, comedy would be important, right? So U4, comedy. So we're just going to focus on these values, right? And again, so we know that oh, sorry, I did this wrong. Sorry. I meant to do it backwards. So this would be sci-fi. Would you agree? This
Yeah.
is romance. You see that? Because these are users, remember? So so actually I'm going to say this is Tom, Bob, Mary, whatever. Right? And so now we're going to say that, you know, these are the concepts that we have, sci-fi, romance, and then these are the users. So we're going to say that in the sci-fi concept, Tom, so let's say Tom now hates sci-fi. Bob loves sci-fi and Mary loves sci-fi. Again, in the scale from 0 to 1, what would be their values, roughly speaking? For Tom, he hates sci-fi.
So like 0.3.
Okay, 0.2, let's say, yeah, low. Bob loves sci-fi.
0.9, 1.0,
Okay, Mary loves sci-fi.
0.9,
0.9. Now, romance. Tom loves romance.
0.9, 0.8,
0.9. Bob hates romance.
0.2,
0.2. Mary is so-so about romance.
0.5, 0.6.
0.5. You see that? That's exactly what has happened. So now, once again, we plot. Oh, sorry. We're just going to do it in 2 dimensions to keep things simple. So we're going to say, you know, this is C1, sci-fi. C3, romance. All right, we once again plot the users. So we're going to plot Tom, Bob, and Mary. User 1, user 2. So let's start with Tom. Tom on C1 is 0.2, kind of down here. Right, kind of down here. But in romance is high, 0.9. So about there, right? So this would be Tom. Would you agree? Then we do Bob. Bob on sci-fi is really high and it's really low on romance, right? So Bob. Mary is really high on sci-fi, so up here. And in romance, she is somewhere in the middle. So she comes to about there, right? So again, you want to recommend some movies, right? You know the movies that Bob and Mary and Tom have rated. You have that from the X matrix, right? You have that in the X matrix because for every user, yeah, this was wrong. It should have been users. Right? So for every user, you know the movies that they like. So you have that. Now, if we go to this example, if we want to recommend movies to Bob, I want to recommend movies to Bob. How do I select which other user is most similar to Bob? Which one would it be?
Mary.
Mary, right? Because why? Calculate the distance. How do you calculate the distance? Just like we did in KNN, the Euclidean distance, or just use that new code that I provided with recommender using the cosine similarity. Either way, it tells you the closest people. So once you know if Bob is selected, right, then Mary is the closest. Okay, Mary. What does Mary like? Okay, then you can now use the other matrices, right, like the X matrix or the movies matrix to make recommendations. Does that make sense, guys? Do you guys see where this is going?
Yeah.
Yeah, that makes sense.
Yeah, and that's it. That's what I want you to do in the homework. So in the homework, just take the code that I provided for recommender systems, and then enable the two functions that I have commented out and use them in this way. And try to convince yourself. That's why I did those dictionaries, right? So that the movies are there. You will know, if I say I give you the Matrix, which I think is in there, then it should recommend sci-fi movies. If you pick a romance movie, it should give you other romance movies. If you pick a what's the other one? Comedy, it should give you other comedies. Okay, but the way that it works is exactly like this. It's nothing more than, you can think of it as a vector space, and then you just have all this information now. Think about it. Initially, you only had the one matrix, right? That's the beauty of singular value decomposition. Initially, you just had the one matrix of users to movies. Now you have these concepts. You have U, S, V. So it gives you a lot more flexibility to complete the task. Okay. So this is the homework assignment. This would be, all the other homeworks I've given you have been pretty easy. This one involves a little bit, but I've already provided the code. What do I want you to show? I just want you to show, as I said, in this one, in a very obvious way, I picked, Professor, I picked, Spaceballs, which was in the database, and it recommended, interestingly, other, wouldn't it be nice? Spaceballs is actually a really nice example, because what should it recommend? Should it recommend comedies? Should it recommend sci-fi, or should it recommend sci-fi comedies? Which of those three?
I mean, technically sci-fi comedy, right?
Sci-fi comedies, right? Because Spaceballs is a satirical version of Star Wars. So that would be a perfect screenshot, right? Like, you tell me, I picked sci-fi comedies, and guess what? A lot of it might recommend a comedy and a sci-fi movie, but a lot of the movies or a good number of the movies it recommended were also sci-fi comedies. So those present the most, the best scenarios to kind of prove the point that it works, okay? That this machine learning algorithm actually does a good job in recommending movies to you. And that's it. That's it, guys. So this actually concludes, our discussion of singular value decomposition, compression, recommender systems. If you notice, we use both, right? Because compression is really just picking that K. So we use compression, and then we use singular value decomposition. And if you think about it, we're also using K and N. So we kind of bring together a lot of things in this one. All right, that's it. Do you guys have any questions?
I do not.
No? All right, so that's basically it as far as the lecture today or the discussion. I really I'm going to stop the recording now.